All right, so in this chapter, and from here on out, trig is going to get a little bit weird. Usually trigonometry gets introduced to you as a way of dealing with right angle triangles. So it makes sense to think of the angles that you're allowed to plug into trig as being between 0 and 90. Now we're going to basically extend this function. We're going to extend this function so that you can actually plug in any real number into a trigonometric function. And the way we do that is we use the xy plane. So what we can do is take any right angle triangle. So what I've done is drawn one right here with a reference angle, or with that angle there, theta. So if we're interested in finding these trig ratios for an angle theta, it's part of a right angle triangle. So we can take its triangle and first of all, draw it so that the angle that we want to deal with here is at the origin. So the theta is going to go in here. It's going to kind of touch the origin. The adjacent side is going to be along the x-axis. So in this one here, that's my 4. So I'm going to draw the adjacent side to have a length of 4 along the x-axis. All right, and that's the positive x-axis, so a positive 4 length there makes sense. And then the opposite side is going to go up from the y-axis, and that opposite side in this angle is going to be 3, and so the opposite side is going to go up, and that should basically complete your triangle for you. So if we draw it like that so that the adjacent goes along the x-axis and then the opposite goes up from there, then we will have that angle that we're interested in should be, essentially it should be made right at the origin. So it's the same triangle. All I did was rotate it a little bit and put it on the xy plane. Maybe you have to flip it around a little bit, do a reflection. It doesn't really matter. What we need though is that the adjacent is your x-axis, and then the opposite goes up from there. And when we do that, what we can actually see here is that because we've gone over 4 and up 3, what we actually get here is a point. So a point at 4 and 3. And so this point here is going to give us more or less all of our information for how we are going to define these trig functions. So yeah, and every triangle that we draw is going to correspond to a particular point on this xy plane. So what we're going to do is kind of work in reverse here for a couple of examples. First of all, we're going to find the primary trig ratios corresponding to the point 5, 7. So what we'll do to answer this is basically draw the point 5 and 7, however we need to do. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Okay, so there's my point 5, 7. I'm going to draw the same type of triangle. So the base of the triangle is going to run along the x-axis. And then I'm going to go up from there to my point and then complete that triangle. And so now I'll just kind of fill in all this information here. So my theta is going to be that angle that goes, again, right up against the origin. So there's my theta. And so if this is my point 5 and 7, what that means is that my adjacent is 5 and my height is 7. And so my trig ratios, I will need to solve for the hypotenuse. The hypotenuse squared is just 5 squared plus 7 squared. 25 plus 49. I don't think we get a particularly nice number here. Yeah, it's 74. I didn't choose this to be great. So yeah, so h will just be root 74. And that should be enough to get us all of our trig ratios. So sine theta, using that triangle there on the left there, is going to be the opposite 7 over the hypotenuse. And we don't have to rewrite that root or anything. It's fine the way it is. I don't think we can actually pull any squares out, but we don't have to rationalize the denominator. So cos theta will be our adjacent 5 over the hypotenuse, and tan theta will be the opposite over adjacent 7 over 5. So those are going to be our trig ratios. So nothing too crazy there. It's just sort of drawing the triangle that goes with this point more than anything. So for part B, we're going to find the angle corresponding to 5, 7. What we can do for this is use any of these equations. I always like to use the tan equation because it comes directly from the coordinates 5 and 7. So what we can do is solve this equation. So if tan theta is 7 over 5, remember we use those inverses to undo this. So theta is going to be the inverse tan of 7 over 5. And I didn't specify units here, so you're okay using degrees if you like, as long as you indicate. And I'm going to get inverse tan 7 divided by 5, about 54.5 degrees. And so yeah, so that's going to be our angle that goes with that 0.57. What we'll sort of move towards though is that that's actually not a well-defined question. There's actually lots of angles that are going to correspond to that point, and we'll see how to get to those later. All right, so what we're going to do now is just take some of the ideas that we sort of just went over about those right angle triangles and try to extend them now, and talk about how we're going to build this language up so we can use it on any angle. So in those equations that we had looked at, and as you can see in the picture on the right here, if we're talking about this angle theta, so we're going to start viewing theta as a counterclockwise angle from the x-axis. So if we start at the x-axis, it moves counterclockwise from there. And so that's why it's always going to be sort of touching the origin. And so if that is our theta, and we draw this triangle to go with theta, then what we're going to have for the triangle is that the opposite is the y value of that corresponding point, that far corner point of the triangle. And the adjacent is the x value of that point. And what we can also do is find the hypotenuse, which will typically denote using the letter r from here on out. R is actually for radius, because you just sort of like draw a big circle around this with radius r. That circle's terrible, but hopefully you kind of get the idea. As theta moves, we don't really want the radius to change. It doesn't really matter, to be honest. We'll just call it r. But we can find that just using the Pythagorean theorem. It's the square root of the sum of the square of the other two sides, basically. Pythagorean theorem. So what we're going to do is just go over a couple examples here to talk about how we're going to extend this ratio. But the conclusion that we can make from here is that sine theta is going to be the opposite, which we've said was y, over the r that we'll calculate using the Pythagorean theorem. Cos theta is going to be the x over r, and tan theta is going to be opposite over adjacent y over x. So we will have these nice relationships that we can use. You may like these relationships, or you might like the pictures that we're going to draw, but we have this. So this is essentially how we're going to extend everything. So for this next question, we've got the primary trig ratios corresponding to the point -12 and -5. What we could do is actually just plug all of this right into these formulas, but I do want to draw out what they're going to look like. So if we draw -12 and -5, that's going to come in the third quadrant. So if you're counting quadrants, I might just jot them down in blue here. So I'm not going to formally go over this, but you'd have a Q1, Q2, and you work counterclockwise, Q3 and Q4. So when both of those are negative, we're going to be in Q3. So at the point -12, too lazy to write all the ticks now. So let's say -12 and -5 should go down here. And if we have a look at this point, essentially what we're going to do is follow what I had talked about before about that x, x is going to essentially follow the x-axis, that x value. And so if I were to draw that out here, I'm going to take x is the x-axis. So we're no longer just going to be looking at lengths. What we're actually going to look at now is it's a directed length. So it has both magnitude. That bar is a magnitude of 12, but it has a direction. So I'm actually going to label it with -12. And then we're also going to have the opposite, which is going to go up or down. So before I said up from the x-axis, but in this case, it has to go down to get to that -5 point. And so I'm going to label this as -5 because it's going down. Oof, that's not what I wanted. And then we also need to get our hypotenuse, the r there. I did choose this one to work out nicely. So if I want to calculate r, it's just the Pythagorean theorem. Make sure you square those negatives to make them vanish. We should get 169. So r is going to be always the positive root of that. We don't want a negative hypotenuse. That's the only thing that will always be positive is your hypotenuse. And so what we get is this triangle, this weird looking triangle with negative sides like that, but they're gonna fall in line with this sine theta is y over r, x over r, and y over x. All of that's gonna come together if we include sines in our triangle picture here. So what we're gonna have is sine theta is y over r, which is, you can either use the y from the point is -5 over the r, which is the root of 12 squared and 5 squared, 13, or you can just use that picture with this angle right here. And the next one is going to be cos theta. So that is x over r. So again, you can just use the x of the point as -12, but it does correspond with the adjacent of that theta in the picture there. So -12 over 13, and tan theta is going to be y over x, which is, well, yeah, either point or picture. So -5 over -12, and that's going to be 5 over 12. So now that theta, I should be careful with that. I labeled that as theta. That's actually not theta. So I have to make a little fix on that. That's actually going to be what we'll call theta r. So we'll talk about that a little bit more in the next video, but that's our reference angle. It's not actually theta. So what we want for theta, as mentioned, as I set up here, theta will always start at the positive x-axis and make its way around. And so we'll try to bring all of this together a bit more in the next lesson. But the angle is always going to start over here and make its way around and then go to basically the end of that triangle. So I wanted that to be in red. I want that to look exactly like the other picture there. So yeah, so what we want for theta is for it to actually just follow this. And we know that this little angle in here is my theta r. And so this is how we put all this stuff together. It's a lot to take in, but what we can do is find that theta r, the reference angle, and that's going to be using one of these equations over here on the left. So again, I'll always pretty much choose tan to solve these. I know that tan theta is 5/12. So I'm going to use the inverse tan on this. Not in. So I'll get theta is about 22.6 degrees. That is actually, now I want to be careful here. Like this is clearly not correct. So this equation that I set up was for tan theta. I'm trying to solve for theta r, the reference angle. Now there's a bit of a problem here. So I got this 22.6. My snag is that specifically, more than anything, tan is not a one-to-one function. And this is like all stuff that we're going to discuss really intensively throughout this whole chapter. Tan is not a one-to-one function, which means that this inverse is not well defined. So all that we're getting is some angle with tan theta is 5/12, not necessarily the angle that we're looking for. And if you look at theta in this picture, the theta that we want is definitely bigger than 180 degrees. Right? 100 degrees would be the flat, and then there's plus a little bit more at the end there. So this is clearly not theta. What we've actually solved for here, this 22.6 is actually the reference angle. Because if you look at this triangle that is made with theta there, if we ignored the signs and redrew the same triangle, so with theta r, so I'm not going to draw this particularly well, but so if I just pretend this is a regular run-of-the-mill triangle and I write my sides, they wouldn't have signs. They would all be positive because I'm no longer like in this weird orientation place of the XY axis. It's just a regular old right angle triangle. If I set up tan theta r is 5/12, right? That should make sense if I look at that picture. And so this equation is actually giving me theta r is 22.6. So it's a little bit of work to actually get theta. But if you have a look at the picture, what you can see is it's this flat section plus theta r, right? It goes the 180 plus another 22.6. And so it's 202.6 degrees. So that is, that's kind of the big picture of everything that's going on here. So it's quite a lot to take in. So I'm going to break it down with another lesson, taking slightly a different approach. But this is how we put our angles on the XY plane and how we correspond them to points.